So for this next learning module, we'll cover kind of the basic topic of Chapter 3, which is how to draw a free body diagram of a body that can be modeled as a particle. In addition, we'll talk about how we can model the types of forces that are applied on the body by support structures that we'll see routinely throughout a lot of problems in the textbooks, particularly how do you model the force associated with a rope, which is connected to a body. In addition, we'll talk about the forces that are exerted by springs. So I'm sure that all of you have seen free body diagrams before. So rather than go through all of these bullets, I'll just put them all up and I'll say a little bit about what a free body diagram is. So first and foremost, maybe the most important thing to focus on is it's a modeling tool that allows us to compute particular forces that may be of interest to us. So if you think back to the first lecture that we did in the class, right, we're not physicists, we're engineers. So we're often going to be asked whether or not a particular support structure is suitable for the given characteristics of a load that it's trying to support. Meaning if you're trying to hold something up, you know its weight, maybe you're going to support it using this different configuration. Is this rope good enough? Is this spring good enough? These sorts of questions. So what we're trying to do is be able to draw some sort of modeling diagram that will allow us to answer those analysis questions of interest and eventually later in your engineering career actually move to doing design, which is a little bit of a harder problem. So when we're talking about the statics of particles, usually at least my free body diagrams come in two pieces. I first start off with saying, hey, I'm interested in finding the force that exists in that cable when it's actually supporting this body. So I will kind of cut away, right, the body of interest, and I'll segment all of my geometry in such a way that I isolate the force that I'm trying to find. And then I will draw all the forces that are acting on the body kind of within that isolated portion of the structure. And if it just so happens that all of the forces lines of actions go through a given point, meaning that we have concurrent forces, as we mentioned in the previous learning module, and we can actually model that body as a particle, well, why would I keep kind of all that detail, all that geometrical detail around that I had in my original drawing? I'll just simplify my free body diagram to just be a single point upon which all the different forces of interest are acting. In general, there's lots of forces that we'll consider in this class that act on a body, but you can kind of view them as being segmented into loading due to the weight of an object, additional loading or applied force that's applied to an object, along with kind of those supporting forces that are exerted by support structures. So when we have a free body diagram, right, we're just drawing vectors, and vectors are characterized, particularly we're drawing force vectors, and they're characterized by magnitude and direction, like all vectors are, along with the point of application. Well, the point of application is really simple if we're modeling it just as a particle. So really, all that we need to describe is the magnitude and the direction of each of those vectors. And there's going to be physical rules that we have to be consistent with. For example, when we're describing the weight of an object in a two-dimensional modeling problem, which your book gives this weird kind of title to of coplanar systems of forces, we're going to always assume that if the body is symmetrical, that the point of application is right in the middle, right, due to the center of mass, which we'll cover a little bit later on within the course. But in addition, we're going to know that its direction is in the minus j hat direction, and that its weight is whatever is specified within the problem description, or maybe that's actually a quantity we compute. We'll have rules that we'll talk about a little bit about later of how to specify some things about the magnitude and direction of forces that exist in support structures like cables or springs. So we just have to be consistent with kind of the models that we're using for those basic types of bodies. Sorry about that. So free body, that term just comes from, because ideally when you do that kind of initial portion of the modeling, you have this drawing that represents the entire problem. You kind of draw lines and just take a portion of that drawing out. And ideally, where you've segmented, you're able to see vectors that correspond to the quantities of interest to you. And they're going to be boring in this chapter because they're just going to be forces exerted on a particle. So sorry about that. The first item that I wanted to talk about that I'm sure all of you are familiar with is a spring. So the book quantifies that we're talking about linear elastic springs. If you're going on to a four-year program or going into graduate school, what the linear term means is basically that. So if a system is linear, it satisfies superposition and homogeneity. An easy way to say that is the restorative force, which we'll define in a minute, doesn't depend on the amount of displacement. But what does the spring do? Well, basically, if you stretch it, it exerts a restorative force, which means that it tries to get back to its original unstretched length in a manner that's proportional to its displacement, or how much you stretch it. So that's what we have going on in this diagram. We see that, and let me kind of go and introduce some additional terminology that your book uses. This L sub 0, they're calling the unloaded length, and that's would kind of just be the length of the spring if there was no applied force to it. If I apply a force F, depending upon the stiffness of the spring, right, I'll have an additional displacement, which here I'm denoting as plus S. And in the traditional coordinate systems we would use, this is in the minus j hat direction. So what happens when that spring is actually displaced? Well, since it's stiff, it wants to go back to its original length. So I'll have a restorative force induced, which is proportional to that displacement. And that's where your usual F equals Ks formula shows up. So it's a really, really simple formula, meaning that how much restorative force do you get? Well, it's somewhat related to how much you displace it. It's a linear relationship. In addition, the constant of proportionality will affect the magnitude of the restoring force as well. So that's on the magnitude side of things. How do you know what the direction is? Well, just know it's always trying to go back to its original length. So in this example, if the applied force generating the displacement is down, the restorative force will be up. That's when you're stretching the spring. If you're compressing the spring and actually applying a force in the upward direction, it's going to apply a force downwards, again, to try to get back to that natural unloaded length. So hopefully everyone's seen that before, and this will just be a little bit of review. So let's talk about cables and pulleys. Particularly, we're only going to talk about cables at this particular point. Hopefully, everyone has some intuition behind pulleys and what their use is. If you need to exert a force in one direction and you can't do it for whatever reason, you can kind of use a pulley in order to allow you, in this particular example here, right? Maybe I need to basically pull an object up at this particular angle, but it's easier for me to just pull down. I can use the pulley to basically redirect the force in the way that I want. So if I do have cables for purposes, or ropes, or whatever you may call them, for purposes of our class, we're first of all going to assume that they don't deform, that they're a fixed length, and also that their weight is negligible. And that's just going to make our modeling easier. Another thing that you naturally know about a cable, if you just hold it in your hand, if you kind of pull it apart, we'll see later in the course that that's called actually placing the rope in tension, right? By Newton's third law, there's a reaction where it tries to basically oppose the pulling apart and pull back on you. So I wish I had a rope in front of me, but I don't. Assume my pen was a rope. If I pull outwards, right, by Newton's third law, there's a reaction force pulling my hand back inwards. So if I have a rope, though, I can't do it with the pen. That's if I'm putting it in tension, pulling it outwards. What if I push it in? Well, if I push it in, it's just going to collapse, right? It can't basically oppose a compressive force. It can only be in tension. So since the rope can only be in tension, forces applied by a rope on an object are only going to pull them up. And we'll look at that in a minute. The other thing that I wanted to say is, if you think about it, and we'll get to this a little bit later in the course when we talk about internal forces, the tension, if I were to kind of draw a free body diagram and segment the rope at any point, the tension in the rope or cable has to be constant throughout. And what that basically means is that the cable is not going to shred. And that will make more sense later. But long story short, when you draw your free body diagram, wherever you cut the cable, you can assume that the tension is uniform throughout. Last type of kind of force that describes the interaction of a body with another body that's discussed in this section of your text is the idea of a contact force. So if I have a cylinder that's resting on an inclined plane, we already talked about this in the prior learning module, but if that is a smooth surface, which is a fancy way to say we can ignore friction, what we know is that the inclined plane will exert a force on the cylinder, which is normal at the point of contact. And I've put point of contact there in quotations because if you think about back to the lecture that I did in chapter 1, we know that it's not going to just sit perfectly at one point. There's going to be some infinitesimal, non-negligible area over which the contact is made. So really, it's a distributive force that we're modeling as existing at a single point, but that's okay. Recall, what do we mean by normal? Well, we mean perpendicular to an axis that's along the surface of the plane. So here, if this plane is inclined 30 degrees from the horizontal, it's normal. So you think about if you had your normal XY plane, if you incline the horizontal 30 degrees, then relative to what was the vertical, the perpendicular or normal force will be 30 degrees inclined here as well, as you see. So I hate to even put a procedure for drawing a free body diagram up here because it's not like, I'm sure many of you have done it before in physics, and it's not one of these things that the first few times you're doing it, you kind of have an instruction manual that you're looking back on. But as we mentioned, it's a free body diagram. So the first thing we do is find out which forces we're interested in. And if we're just in general asked to kind of model a particular body in equilibrium, we'll draw in our drawing a box around it, and we'll separate it from all of its support structures. And then what we will have left, ideally, is the body of interest along with portions of the various support structures that we're acting upon it. And based upon the rules that we have from the previous slides, whether those support structures are ropes or whether they're springs, we will know something about how to model the forces that are exerted by each of those. So kind of once you have your body of interest separated from the original drawing and you go back and sketch it a little bit, look at all the forces that would be exerted on that body. Hopefully, depending upon your particular problem, you likely have the weight of the body itself. You have additional loading forces that are being applied. And if the body is in equilibrium, you have supporting forces that are counterbalancing the weight and the applied forces. What we want to do then is actually draw a vector corresponding to each of those support forces. And we have to kind of obey the modeling rules that we looked at in the previous slide. For example, it wasn't in a previous slide, but in 2 dimensions, the weight will always go in the minus j hat direction, and we'll always kind of apply it at the center of mass. We'll either be told what that is, or we'll just assume geometrical symmetry, and we'll put it right in the middle. If we have a support structure like a cable, we will know that the direction of the force is going to be along an axis defined by the cable itself. We'll know that since the cable has to be in tension, that means that the cable or rope is pulling outwards on the body. That's the only way it will work. So we actually can say something about the direction in that case. If it's a pulley type problem where we've segmented a cable at 2 points, we know that tension is uniform throughout the cable. So just obey all those physical rules that we talked about in the previous slides. And the one thing to keep in mind, once you kind of describe all the forces acting upon your body, first and foremost, if they're all coplanar, you can model it as a particle. You can simplify your drawing and just draw a point and kind of make life easier for you. But in addition, one thing to keep in mind is if you're working in 2 dimensions, the necessary and sufficient conditions for equilibrium, going back to the last learning module, are just that the resultant force, which will be a 2-dimensional vector, is 0. If you think about what it means for a vector to be 0, that means that each of its components are 0. So in 2D, you got 2 equations. Generally speaking, from a linear algebra point of view, that will allow you to solve for 2 unknowns. When we move into 3 dimensions, we'll have the capacity to solve for 3 unknowns. But again, we're going to be restricted in what we actually can determine through this back of the envelope type analysis. So what I'd like you to do now, and I'll make an announcement about it here in a minute, but for the part 1 homework of chapter 3, rather than assign actual kind of typical homework problems, I just assigned 2 different tutorials. And the first tutorial is going to give you some experience in actually drawing free body diagrams within the MyLab software. So I'm going to try, hopefully I can, I have this up still. Let's hope so. Yeah, here we go. So here is the first problem that you'll be solving. So what we have here is some type of cylindrical mass that's being supported by cables, which are attached to springs. And what you want to do is just walk through step by step. And let me see if I can actually, if you go through like the available hints and whatnot, what I wanted to show you is, they're kind of going to walk you through step by step. That way you don't have to, hey, how do I get started on this? So this is just right triangle trigonometry, right? This is a right angle. So we can relate these side links to these angles using our trig functions, specifically for both theta and phi. We know the opposite and adjacent side links, so we can relate them to tangent. Just be careful when one of the side links is a fraction with your algebra. In addition, this is the one that I really wanted to show you, and I kind of was just playing. I'd never used this beforehand, so I was just going around and drawing the vectors myself. Let me see. Well, let me delete this. No. Yeah, well, okay, cool. Delete. Come on. So anyways, this interface, if you notice, you can set the both the angles along with the magnitudes. So what you want to do there is just get some experience with the drawing. Sorry, I'm stuttering here. I was hoping I would actually be able to show you how to do that. Oh, here we go, standard view. Maybe everyone wants me to pull up the solutions view. So if you're in the view of the standard view that you have, and you go, the main point I wanted to show you is drawing this this free body diagram. The reason I'm not giving you much homework here, in addition to the fact that you already have the chapter 2 homework, is I want you to get some experience actually kind of seeing how to draw vectors and free body diagrams in this software. So we'll do the easy one. How would you describe the weight of this body? Well, we're going to have the point of application be the center of mass, which we'll just assume will be at the middle here, that this is a uniform cylinder. And we'll have the angle here be 270. Why 270? Well, remember that by convention, we measure from the positive x-axis in the counterclockwise direction, going from positive x to y is 90, to negative x is 180, down to negative y or negative j hat is 270. So I'm not going to say too much more about this because I think you all will be able to figure it out relatively easy. But if you do have any questions, just do please let me know. And hopefully I'm not giving you too much for this week. If I am, just let me know, and we can extend any of the deadlines. So I'll talk to you soon.